See, last semester I had a problem with about 5 people coming late at my A15 class, and pretty much all of those people did poorly in the class. So I'm going to encourage people to come to class on time, and the way to do this is to give you guys a gentle nudge with this quiz, which is probably 5 points at the moment. So let me get this out of the way here. All right, so here's the attendance sheet. I try to keep things on this, so if you can check that. That way I don't have to worry about when Top Hat doesn't work for you, as inevitably it will for about 10% of you in a given semester, right? So I never want you to put you in the place where when Top Hat doesn't log on, you have to get your computer out, and you've all done this in a large lecture section. At no point do I want to have this problem for you in here, which is why we have the paper backup. But I do have to take Top Hat. All right, so let's talk about first order. Ordinary differential equations. So basically, we're talking about, man, this particular marker just does not come off. There's like marker smudges from last week still up here. I think this particular pack of like black markers that we have in the math department, they must be like old, and they're just leaving like crumbs. All right, anyway, so here's the deal. We're looking at solving the problem dy dx equals to f of x comma y. Sort of generically speaking, this is a first order differential equation. All right? So it's a differential equation which meaningfully involves the first derivative with respect to x. And it's got some expression, right? And there are different kinds of first order differential equations that are easier or harder to solve, right? So we can trade this is equivalent, well, mostly equivalent, to something like this, right? F dx minus dy equals to 0. So if I call this thing star, this is the so-called Pfaffian form. I can't spell Pfaffian. I forget. There's two F's one of those places. It doesn't matter. He's not here. So it's probably, I don't know. Anyway, this is the Pfaffian form. And so like, sometimes we write the differential equation in that notation. Sometimes we write the differential equation in that notation. We'd like to understand how to solve both, right? So last week, we talked about, more generically, a differential equation sort of in this form, right? Like p dx plus q dy equals to 0. So that's the other way we've looked at a differential equation, something like that. And what did we say? If you can write this, if this can be expressed as like, let's say dg equals to 0, then g of x comma y equals to a constant. This is the solution. I'll call this star star. Now, you guys tell me, what kind of differential equation is that? Exact. That's an exact differential equation, right? So if we can write the differential equation in Pfaffian form as the total derivative of a level function, then it's an exact differential equation, and the solution is simply level curves of this function, right? All right. And we derived that the solution curves to that function are like perpendicular to the vector field PQ, right? That's one of the things we learned. And I started with talking about integral curves, and we'll get back to that eventually. But today I just want to talk about solution techniques for the most part. So there are 3 main kinds that we can talk about. The one is this. We have an exact equation, and we look for the level curve, right? The other more simple kind is when we have that this function here can be written, let's say, so that's an exact equation like you guys just told me. So for an exact equation to solve that, you just need to find the level function, right? And then a level curve is your solution. If we have dy dx equals to, I need some other letters. Let's say, I haven't used anything Greek yet. Let's say alpha of x, beta of y. All right? So we've got a function of x, we've got a function of y, and we can write it like this, right? If the differential equation looks like this, it's said to be separable, separable, it's a separable differential equation. And those are super easy to solve, right? Because we just separate variables and integrate. So to solve this guy, you just do like dy over beta equals to alpha dx. You integrate both sides, and then you got your solution, right? We've seen those. What's the other kind of, for like, basic differential equation we can talk about? Is the so-called linear differential equation. So a linear differential equation, first order, looks like the following. dy dx plus p times y equals to q. My apologies, the p and the q here have no relation to the pq I'm using up in red, all right? I'm just going to reuse some letters sometimes, and you have to understand from context like what I'm talking about, right? So, now that's a linear differential equation, and we haven't talked about how to solve those yet in here. But you should have seen it in calculus too. I don't assume that you're remembering it from calculus too. I'm just saying you should have had some experience with this before, if you had calculus here at least. And the question is, how do we solve these, right? So you can try to solve this as an exact equation, right? Well, first of all, could you try to solve it as a separable equation? What happens? Let's attack it that way first of all. First of all, we get dy dx equals to q minus py. Now here, I should emphasize the p and the q functions of x alone, all right? So if you were to solve dy dx equals to q minus py, can you write it as a product of a function alpha and beta? Like I can't, right? I don't know how to, I can't, there's no way to extract a y from this, right? Without dividing by y, but then I've got y in that. There's just no way to separate variables here, okay? So that doesn't work. The next thing you might try is, well, is this linear differential equation an exact equation? Let's try that out. So, you know, is dy dx plus py equals to q an exact equation? What do you think we're going to find out there? Let's look at it here. We've got what? We've got q minus py times dx minus dy equals to 0. So it's helpful for me to change notation. Let's think of this as the m, right? This is my m, and over here I've got n equals to minus 1. Remember what the closed condition was? We need m sub y equal to m sub x is our closed condition. And that's a necessary condition if this is going to be an exact equation. So is it? What's the partial derivative of m with respect to y? What's that? Negative p, right? And what's the x derivative of n is 0. Oh man, well that didn't go well, right? So it's not an exact equation either, right? So this is neither separable nor exact. We need to find another way. So one of the other ways that you can repair a differential equation is you can introduce something called an integrating factor, all right? And an integrating factor, so if we, you know, this is just a definition, given, let's say, you know, m dx plus n dy equals to 0, not exact, all right? Then I is an integrating factor. Integrating factor if, when we multiply by im dx plus in dy equals to 0 is exact. All right. So if you can find a function such that when you multiply the differential equation by that function, it becomes an exact equation, then that function is called the integrating factor, or an integrating factor. There could be many, right? In fact, if you think about it, if this works, right? If multiplying by I makes this exact, which means what? What does that mean? That means that you can write that Pfaffian form as the differential of some level function, right? That means that this is equal to like dg equals to 0, and then we're off to the races. We know the solution, right? That equal to a constant. Well, think about this. If that works for I, what would happen if I did twice I? What would I get? I would just get that same expression was twice the differential of g, whatever g was, right? Or if I did 10 times I would just get the differential of 10g. So integrating factor definitely can be scalar multiplied by, so it's not unique, right? There's more than one integrating factor if there's one. And actually Pfaff's theorem, which I will not prove in here, but here's a theorem. It says star always has integrating factor if solution to star exists. And so star, I'm talking about the original problem. So literally any first order differential equation, if it has a solution, there exists an integrating factor to make it an exact equation. So in some sense, the notion of an exact equation is general. Now you're like, well, why don't you just teach exact equations? Well, the trouble is finding the integrating factor in general is more difficult than solving the differential equation. So it's not like a terribly useful theorem in that regard. But it is kind of nice to know it's out there in principle. In practice, they're sometimes really hard to find. However, not for this problem, not for the linear problem. So let's look at it. So we've got, we're starting with, let me call this equation here Bob. So multiply Bob by I. All right, so then we have I times q minus py dx minus I dy equal to 0. So the first step in the integrating factor method is to multiply the differential equation by I. I did that. Now, so what do we need? We need what? We need partial y of I times q minus py, right? Equal to partial x of minus I. That's what we need. We need the closed condition to hold, right? Because if we can get that, then it's exact. And by it I mean I times Bob, right? Or I Bob. Now, all right, what would make this easier? How about this? What if I is just a function of x? If I is just a function of x, then we can try to look for a solution in that regard, right? And this is going to be a theme this semester. As we're looking for solutions to differential equations, we can always narrow our search and try to find a simpler solution, right? And if our search is successful, then great, right? If it's not, then we have to go back and reevaluate our choices. So a thing to make this problem a little bit simpler to understand is simply to assume that I is a function of x. So we can make that assumption and see where it takes us, right? So what happens then? And here's my, don't tell the math majors, notation for that, I equals I of x. Which, more to the point, another way to say that is like partial y of I equals to what? If I is just a function of x, then what? 0, right? Okay, so do this derivative up here. What do we got? We've got, well, I times q, what are those? Those are both functions of x, right? So that piece drops out. That's just 0. And we have, well, minus I p partial y partial x. Oh, my bad. What is the partial derivative of y? I'm an idiot. Just a second. Let me. Sorry, guys. So I'll write a step here. Partial y of IQ minus partial y of minus IPY is equal to minus partial x. All right, great. So then what? Well, this part is 0. And what happens with, well, I and p are both functions of x, right? So we can pull those outside the partial derivative. And we just have I times p times partial y is equal to, and we can just write that as a total differential, right? Because I is just a function of x, so my partial derivative with respect to x is really just a derivative with respect to x. Then what?
Shouldn't the left side be negative?
Yeah. Wait a minute. Yeah, I've invented an extra minus here, which was totally bogus. Let's make that a plus, make this a minus, but then they go away. So what we got is I times p equals di dx. So this is the differential equation that our integrating factor, which is just a function of x, supposing such a thing exists, must solve. Can we solve that? Oh, we can. See, this is separable. So what this gives me is di over I is equal to p dx. Integrate both sides. We get natural log the absolute value of I is equal to the integral of p dx, which gives me that the integrating factor is the exponential of the integral of p dx. And of course you could put a constant here. I'll put a constant in since it'll bug you guys if I don't. Well, let me say this. The constant is included in the, that is an indefinite integral, right? So it's adding plus a constant. So there's like an arbitrary constant in that integral factor if you like. Like I just told you guys, the integral factor, if it works 3 times, it works. We don't really care about a constant multiple. And you might say, well, it could be plus or minus. Again, it doesn't matter. We're multiplying the whole equation by it. Anyway, that should work. Now, if you remember calculus 2, that's exactly the integrating factor that we were taught how to solve these problems with. Right? Some of you remember. Nobody remembers. Someone here remembers. Nobody? All right. Am I just bullying you into remember, or do you actually remember?
I do remember.
You do remember. All right. Let's see here. So let's see if we can actually work out one of these problems from scratch. So this is just a derivation. This is why we do the integrating factor method. And so let us look at a simple example. If I can find one. Let me not make it too simple. And what I'm going to do here in this example is I'm going to do 2 things at once. I'm going to work a specific example, and I'm also going to look at the general derivation of the method. All right, so see if I can find a good problem in here. So this is my section 2.2. Yeah, that's a good one. dy dx plus 2 over x times y equals to 3. dy dx plus 2 over x times y is equal to 3. That's a good problem. So there's my specific problem. All right. And over here, I'm going to work the arbitrary one. dy dx plus py equals to q. See, this derivation over here has given us a leg up. We know what we can do. All right. The funny thing is, we're not actually going to solve it as an exact, I mean, after all this rigmarole to make it an exact equation, we don't actually take that perspective when we work these examples. A short calculation would show you that any separable equation can be recast as an exact equation. All right? But in practice, it's just easier to do separation of variables, all right? So we'll do that when we can. Okay, so first order of business here is we'll define the integrating factor as the exponential of the integral of p dx. And that's kind of is as far as we can go here on that one because p is arbitrary, right? But over here we can do it. Let I equal to the exponential of the integral of 2 dx over x. So just the coefficient of y comes into play here. Now what's the integral of 2 over x? By the way, x is just a notation for the exponential function when I don't want to write the argument in a tiny like superscript font, right? Like I want nice big, right? Nice big font to see it. Okay, anyway, so that is what, 2 natural log the absolute value of x, which is the exponential of the natural log of the absolute value of x to the power, absolute value of x to the power 2, which is the absolute value of x squared, which, by the way, is x squared. If you're working a problem and your integrating factor works out to the absolute value of x, simply drop the plus or minus and use x, right? Because the integrating factor is always just up to a multiplicative constant. So don't make it more complicated than it needs to be. If hypothetically in another problem you got like absolute value of x, just keep x. It'll work. And probably you need to, like, in that kind of problem, focus the domain either on like a positive or a negative context. X equal to 0 will be undefined. Kind of like this problem. X equal to 0, not defined. Yep.
How did you get the ln of x? Because I thought the integral of that was 1 over x plus the derivative of ln x.
No, the integral of dx over x is the natural log of the absolute value of x plus a constant, but we don't need to add the constant because if we added the constant, that would then multiply this by e to the c, which we don't care about. So, yeah. But that wasn't your question. Yeah. So yeah, it's just x squared. All right, great. Now, so next, so that's step number 1. Step number 1. All right. Step number 2, multiply. Let's call this equation star. We'll make it famous. There you go. Multiply star by I. So that gives us I dy dx plus IPy equals to IQ. Right? And over here, for this problem, we get what? We get x squared dy dx plus x squared times, what's x squared times 2 over x? It's just what? X squared times 2 over x is equal to 2x. So we get 2xy. And what's 3 times x squared? Well, it's 3x squared. Okay. So that was step number 2. All right. Step number 3. Notice that dy dx is what? What's the derivative of the exponential of the integral of p dx? The product rule is the right idea. You're getting ahead of me. But this at the moment is chain rule, right? Derivative of exponential is what? The exponential again times the derivative of the input. I mean, the input to the exponential. So here we get what? We get like e to the integral of p dx times the derivative with respect to x of the integral of p dx. But what is the integral of p dx? It is the antiderivative, right? So those are inverse operations. We're just back with, I think I heard a p. Very good. And so this is actually I times p. So the derivative of I with respect to x is ip. All right? So notice that I have one of those right here. See that? I have one of those right here. And so therefore, I have I dy dx plus di dx times y is equal to iq. And then that product rule you're just telling me about is that. That's d dx of I times y is equal to iq. So this is, I usually call this the reverse product rule because it's going backwards of our usual method, yeah? So our step number 3 should hopefully be the reverse product rule, right? So step number 3, reverse product rule, which of course you could just call product rule, because you could either read the product rule left to right or right to left, either way, you know. But this right here is, we get what? d dx of what? X squared times y. Now, you should actually think when you do this. What I mean by that is, don't just make this I write down d dx of the thing. Like, actually think through it. If I differentiate what I have there, will I get back to where I started? Right? If I take this derivative right here, right, I will get back to there. You know, I got to think about that. Check it. If that's not possible, what that means is you calculated the integrating factor incorrectly. Or you multiplied the integrating factor incorrectly, which I feel like is less likely. I think you can multiply. Although, this step right here is easy enough to mess up if you're in a hurry. Yeah? So if this reverse product rule doesn't happen for you, you've made a mistake. You need to go back and fix it. All right? So what's step 4? Yeah, step 4 is just to integrate both sides. So we integrate, and I'm out of board space here, but that gives me iy is equal to the integral of iq dx. So therefore, y is equal to 1 over I times the integral of iq dx. Now, some people teach this as like a formula for this problem. I do not teach that. I would not recommend that. I'm going through this process because this process is what you should do to solve these problems, because there is a error check built in. Yeah? If the reverse product rule doesn't work, you didn't do it right. So for us, integrate both sides, what we got? I'll write it out here since I got more room. d dx of x squared y dx is equal to the integral of 3x squared dx, which gives me what? So the integral of a total derivative is just the function again. So I've got an x squared y there. And what's the integral of 3x squared? I believe it's x cubed, right? And at this point, you got to add a constant. Remember last week I talked about adding a constant at the end being foolish and not nonsensical? I was talking about this. I was talking about waiting past this step to add the constant. We add the constant now. This is where the integration happened, plus c. You could add it on either side. You could add on both sides, but I would recommend just adding it over here, right? Yep.
Since I comes from integral, should there be a c at some point there?
If I added a constant in this integration, right, what would that have done? We would have like integral the function that we have plus a constant, right? That would just make us multiply by e to the c, which then we could just divide by later. So like there's no need. So this integration is conceptually different than that, though, you see. And okay, so like at this point, let's talk about some name calling. If I just say solve the differential equation, and I'm not careful to tell you find the explicit solution, you'd be by rights to just put a box around this and say solved. You could do that, right? This is a implicit solution to the differential equation. All right? I guess I should make it star star. There we go. If I had an initial condition, right? If I also told you like y of 0 was 3 or something, we wouldn't be done, right? We'd actually have to put in that information to figure out what the constant had to be, right? But we weren't given that, so this is the implicit general solution. Like any x and y which solves this equation for some c is on that particular solution set. Now, what's an explicit solution? Explicit simply means solve for y. So that's easy enough to do here. Y is equal to x cubed plus c divided by x squared, of course, which we could write as x plus c over x squared, right? So y is equal to, my bad, x plus c over x squared. This is right here. This is an explicit solution. So explicit solution means you need to solve for y. Implicit, I don't put that on you. If I just say solve, you know, that means you can leave it implicit. All right? If I forget to say explicit, it's on me. You know? Now, I think this is probably just for me. I think if you look at the space of all possible differential equations instructors, you'll find that generally speaking, when they say solve, they mean explicit. So I'm just trying to be nice. All right? So, yeah. It's too early for you guys to recognize my niceness, I understand. But anyway, this is the integrating factor method. Shall we do another? See if I can find another. Actually, I don't have, my notes only have like two problems here, unfortunately. If you go to the, if you want more examples of this particular topic, if you go to like my, you know, the differential equations webpage, and if you look at the solution, the problems I have solved from, like, you know, the textbook, there are like 1, 2, 3, 4, 5 problems solved in there. So I'm just going to go in there and look up one of those. Yeah, this looks interesting. Let's solve dr d theta plus r tangent theta equals to secant theta. Yep.
All right, if you don't specify and we give the explicit solution, will we get credit?
Yeah, I'm not saying you have to give the implicit solution.
I know, I'm just saying, but if you don't specify, it's okay if we go all the way through.
Well,
I realize that the solution is in there, but if we circle the wrong solution,
I mean, every explicit solution is technically also an implicit solution. So, yeah, I mean, I would.
It's a weird question. I was just wondering.
What I'm trying to say is, like, this is the more general thing. So if you give this, it's still an example of that. I mean, there's not a unique implicit solution. Like, there's the whole. You could take this and do any number of things to it, and it would still be an implicit solution. Like, it's a somewhat cagey thing I'm saying, but like an implicit solution to the differential equation is simply an algebraic equation whose differential consequence is the differential equation, whatever that means. Like, differentiating the equation gets us back to that, I suppose. But will I take points off? I mean, if you follow instructions, you should be fine, I think. So the bigger question is, like, was initial data given? You know, that's a bigger issue. Let's see here. What did I say a second ago here? But, you know, do feel free to ask questions. It's good. It's good. I hope did I answer your question? I think I did. So this business right here we did not do in Calculus 2, right? In Calculus 2, we just pulled the integrating factor from where? Principle of mathematical magic, right? So this is some derivation. And you might wonder about other integrating factors, like what are the methods to find other integrating factors? I don't do that. This is as far as we go in this course for the most part. Like, there's another homework problem you might have where I give you the form of the integrating factor and you have to figure out the specific choices of, like, the exponent or something like that. But pretty much that's just an invitation to use the closed condition to pin down the specific choice of integrating factor. The larger question of how to find integrating factors is really beyond this course, and it really belongs to what's called the method, like symmetry methods in differential equations, which is an interesting topic in its own right, born of physics. Like, usually in physics, differential equations have special solutions which are obtained by choosing coordinates that are suitable to the problem. And usually, if you choose the right system of coordinates, things get much, much nicer. So here's another problem.
So this is example 2.
Example 2. And so, like I said, I have a few more examples. If you look at the web page, I have like a table where I have solved homework problems from the book. This is one of those. It's like page 2 in that PDF of 3 pages. Let's get to it. Anyway, so is this linear, first of all? You might be like, well, it's got a tangent of an angle. That's not linear. Well, that's true. When we say linear, what are we talking about? We're talking about the dependent variable and its derivative, appear linearly. So here, r, rather, is the dependent variable. You have this, you have that, so we just need to interpret things. This is my p, this is my q, and so my integrating factor should be the exponential of the integral of tangent theta d theta, which, let's see here, let's do that. That's the integral of sine theta d theta over the cosine of theta, which is the exponential of the integral of minus du over u, which is the exponential of minus the natural log the absolute value of cosine theta, right? Which is the exponential of the natural log of the absolute value of secant theta, which is the absolute value of secant theta. Absolute value of secant theta, I'd say just drop the absolute values, and we'll just use, we'll try, let's say, an integrating factor of secant theta, see if that works for us, okay? It's going to work. All right, so then what do I got? Multiply by I by secant theta. I've got secant theta dr d theta plus r tangent theta secant theta is equal to secant theta times secant theta, also known as secant squared theta. Well, I think this worked out nicely, right? Because what is the derivative of secant? Right. So this right here is the derivative with respect to theta of secant theta, which is what we should hope for, right? So then reverse product rule, we have d theta of secant theta times r equals to secant squared theta. Sorry, I'm an idiot. I should have jumped in that pool. I was offered $100 to jump in a pool this weekend, and I hesitated. I was like, I wasn't sure, like, Dr. Putney was actually going to, I feel like he was going to, like, he's going to say, I had a minute to do it. I feel like I've jumped in the waters. You'd be like, haha, you waited, that was 65 seconds, like, the money's still mine. It's like, there's like a math pool party now. This is why you should be a math major. We have pool parties. Do you have pool parties in engineering? No, because engineers are lame. They have no pool parties. Just saying. Anyway, just kidding. I love engineers. Somebody's got to drive a train. But sorry, that's an old joke at this point, I think. I mean, who drives a train anymore? But I'm just kidding. So there we go. The reverse product rule worked. Now we can integrate both sides. Yeah? So integrate. This side is easy. Secant theta times r, right? And the other side, well, so I always feel bad for Calculus 2 students when I see them spending a lot of time on this integral. And I've seen it. Maybe you've been in this place yourself, right? Where you're trying to derive the integral of secant squared. It's a bad place to be, right? Because this is an elementary integral, right? This is one of the basic lists of integrals that we know because we know derivatives and we know that this is tangent. So there you go. And then solve for r. We'll get r is tangent theta plus a constant divided by secant theta because I decided I want to get a explicit solution, and there you go. That is the integrating factor method. When should you use the integrating factor method? Do you guys want to tell me?
Other things don't work.
When the other things don't work, right? There's an easier answer. I mean, that's true, but the easy answer is if the differential equation is linear. That's it. When is the differential equation linear? If it specifically has the form dy dx plus p times y equals to q. Now, it doesn't have to look like that, right? It could look like this. It could look like dz d alpha plus h of alpha times z is equal to g of alpha. Like, this is a differential equation, which is linear. The dependent variable, so z dependent variable, alpha is the independent variable. In this context, what would you make your integrating factor to solve such a problem? We need to talk about this because we don't know how if x is our independent variable, right? You need to understand that these recipes that I try to teach you in this course, they have to be adjusted according to like the conditions on the ground, right? You got to recognize what's the independent variable and, you know, proceed accordingly. So here, my integrating factor I would use would be exponential of the integral of h of alpha d alpha, like that. I would do that if this was the problem. You know, more often than not, it's either t or x for us in here, but we do thetas sometimes. So we'll do more examples, but these are the three main kinds of differential equations that you have to face: separable, exact, right, or linear. And I have a little bit more to show you about exact. Like, there's a slick formula for solving an exact equation in terms of doing specific integrals. I'll talk about that next time. In the time that remains, I want to show you the fourth method. The fourth method is substitution. And substitution has a lot of different forms. I'm going to work one which is, I hope it's interesting. We'll see. So maybe you guys will tell me how to solve this problem. Let me get the problem out in front of us and see if you guys have any ideas. All right. dy dx equals to tangent theta times the square root. Oh, tangent theta, what's wrong with me? Okay, I just gave it away. Inverse tangent of y over x. Oh, that's not what I want. I'm sorry, guys. I'll get it together here eventually. Making up the problems is the hardest part, you know? The good news is you almost never have to do that in this course, you know? I mean, I guess on occasion I'll ask you guys for an example of a differential equation which has a certain solution, but that's kind of like a second order question, you know? We mostly just make you guys solve them. So let's see here. I'll get it eventually here. Suppose we have dy dx is equal to y over x times the square root of x squared plus y squared. Yeah, we'll try this. I may have made myself something too horrible, something too hideous. Now, so like, and then, oh, times the inverse tangent of y over x. There, now it's horrible. Now for sure, for certain, we do not want to try separation of variables, right? And we don't want to try exact equations. We don't want. It's not even linear, right? Square root of x squared plus y squared. All hope of linearity is lost here. Oh, inverse tangent of y over x. That's also not linear in y, right? So I think this is going to like confound all of our methods, but it does scream at you a particular thing, what does it say to you? Anything?
Switch majors.
Switch majors?
Trig substitution.
Trig substitution is kind of on the right idea. I think this differential equation should be, maybe if we change to polar coordinates. If we change to polar coordinates, things may go better for us, right? So some of that's easy, like x equals, so let's here are the rules of the game. X equals our cosine theta, y equals our sine theta. Yeah. And so we also know that like inverse tangent of y over x is equal to theta. And we know that the square root of x squared plus y squared is equal to r. And I'm going to be kind. I'm going to say that the context here is x greater than 0, just so we can not quibble over definitions of angle and such, right? So, all right, would that help? I mean, that kind of helps. We've got dy dx equal to y over x. This is an r, right? That's a theta. And hey, what was y over x? So we've got r theta. That's a tangent theta. Yeah. And so I could trade this for like a dy is equal to r theta tangent theta times dx. Now both x and y respectively depend on r and theta. How do they do that? This total differential thing we teach you in Calc 3, it does all the variable change for you if you just let it do the work. What I'm saying is dy is what? Take the differential of y, what do you got? You have sine theta dr plus r cos theta d theta is equal to r theta tangent theta, parentheses, what's dx? Well, dx is cosine theta dr minus r sine theta d theta. Now we have a Pfaffian form in r and theta. Perhaps we could solve it. I don't know. I just made this problem up for you guys, So that's like group stuff. What we got? We've got ourselves a sine theta minus r theta tangent theta cosine theta dr, right? Plus parentheses r cos theta plus r theta tangent theta sine theta d theta equal to 0. Boop, boop, ba, ba, ba. Well, some of these things simplify a bit, right? Like tangent theta times cosine theta is sine theta. So we can simplify this first term here to what? Sine theta times 1 minus
R theta.
yeah, r theta dr plus anything. Well, we can factor an r out there. R. And, sorry, I'm still an idiot. Yeah, well, it's a cosine theta. Yeah, it's not looking good for us, guys. Plus r theta sine squared theta over cosine theta d theta equal to 0.
Could you, before doing that, cancel out tangent and inverse tangent using the y over x tangent theta?
Oh, well, that's not that kind of inverse tangent. See, you're thinking of cotangent. So like inverse tangent of y over x, we have to hit it with composition of tangent to get y over x. But like 1 over tangent is cotangent, which is not this thing. It's inverse with respect to function composition, not with respect to multiplication. Anyway, I think, so anyway, I was trying to illustrate a method. I'm sorry I didn't give us one that worked out all nice and pretty. I was trying to make it. I was hopeful that, anyway, it didn't work. So you win some, you lose some. I'll shut up. Thanks, guys.